In these videos, you will learn how to solve a numerical example on continuous beam using four different methods. That is flexibility matrix method, moment distribution method, Carney's method, and slope deflection method. After watching this video, you will understand how to draw a shear force diagram and bending moment diagram of a continuous beam having all simple supports. You will also learn how to locate position and magnitude of maximum bending moment, and how to locate the point of contraflexure. In this video, we will solve this continuous beam using flexibility matrix method. For other methods, I will provide the link in description box. Video. I assume that you know the basic equation in flexibility matrix method. In case, if you are not aware of this equation, you can watch the video on basics of flexibility matrix method first. I will provide the link in description box. Flexibility matrix method is a force method, and therefore in this method the step 1 is to calculate degree of static indeterminacy. Let us calculate degree of static indeterminacy. In this case, there are four unknown support reactions. Number of equilibrium equations are 3, and therefore degree of static indeterminacy is 4 minus 3, which is equal to 1. Next step is to identify redundant reaction in the structure. Degree of static indeterminacy in this beam is 1. That means there is one redundant reaction in this beam which cannot be calculated using three equations of equilibrium. Therefore, we have to consider any one vertical reaction as redundant reaction. In this case, I am considering RB as redundant reaction. You know that the basic equation in flexibility matrix method is dr is equal to DRL plus F into R. Let us understand the meaning of each of these terms. The first term is dr. Dr means displacement in the direction of coordinates or displacement in the direction of redundant reactions. So here the size of matrix will be ds by 1. In our case ds is 1, so dr will be 1 by 1 matrix. Next term is DRL. DRL means displacement in release structure due to load in the direction of coordinates, in the direction of coordinate or in the direction of redundant reaction. Its size is also ds by 1, where ds is degree of static indeterminacy. So in our case it is 1 by 1. Next is flexibility matrix. Flexibility matrix is nothing but the displacement in the direction of redundant reaction due to unit force. So its size is ds by ds. So here ds is 1, and therefore size of this matrix is 1 by 1. And the last one is R matrix. R means redundant forces, which is RB. Its size is ds by 1. So in this case it will be 1 by 1. So now let us develop all these matrices for this given continuous beam. First, we will develop matrix of redundant forces, that is R matrix. Since we have considered RB as redundant force, so R matrix is nothing but RB. Next, we will develop DR matrix. DR means displacement in the direction of redundant force. So since at the redundant force, displacement is 0 because there is a support, and therefore here dr will be 0. There will be value only if there is sinking of support for this matrix. Otherwise, this value will always be 0. Now to develop DRL and F matrix, we have to use some method to calculate deflections. DRL means deflection in release structure due to load, and F is also a deflection due to unit force. So you can use any method. If you want to use conjugate beam method or moment area method, you can use it. But here I am using unit load method to develop DRL and F matrix. If you want to develop DRL and F matrix using unit load method, first of all, you have to remove the redundant. Redundant is RB. That means you have to remove the support at B. If you remove the support at B, the beam will become a simply supported beam, which is supported at A by roller support and at C by hinge support. There will not be any support at B. We are removing support B. After that, we have to remove the load and apply the unit force in the direction of redundant, and then we can develop DRL and F matrix. So let us see how to develop DRL and F matrix. So now first of all, we will redraw this beam by removing the redundant force. So we will remove the support at B. The beam will become a simply supported beam which is supported at A and C. After that, we will draw a beam with unit load at B in the direction of redundant force. The first beam, we call it as capital M diagram, and second we call it as small m diagram. In unit load method, we have to write the bending moment equation, general equation of bending moment for different part of the beam. In this case, there are three parts, that is AD, DB and BC. So we have to write the general equation of bending moment for M diagram and also for small m diagram. So to write the bending moment equation, first of all, we have to calculate the reactions at support at A and C for capital M diagram and small m diagram. Let us first calculate reaction at A for the given load for first beam. So for that we will take summation of moment at C equal to 0. So RA into 10 minus 40 minus 60 into 6 is the load and it is acting at 3 meter. So is equal to 0. We are considering clockwise positive and anti-clockwise negative. So if you solve this, you will get RA is equal to 112 kilonewton. After that, for first beam, apply summation of vertical forces equal to 0. You will get RC is equal to 248 kilonewton. Similarly, we can calculate reaction at A and C for second beam due to unit load. So we will get RA is equal to minus 0.6 kilonewton due to unit load. Minus means the reaction is downward. Again apply summation of vertical forces equal to 0 to second beam. We will get RC is equal to minus 0.4 kilonewton. Minus means reaction at C is in downward direction. This is how we calculate the reactions for beam 1 and beam 2. So we have calculated the reactions at support A and support C due to given load and due to unit load. Next step is to prepare the table. So you have to write portion, origin. M means bending moment equation due to load and small m means bending moment equation due to unit load, limits and I. So we will write the general equation of bending moment for various part of this beam. This beam is divided into three parts, AD, DB and BC. So first of all, we will write the equation for portion AD. Now first we will write the equation for portion AD. For portion AD, we will take A as origin. That means we are measuring X from A. Capital M means the bending moment equation for first beam. And small m means bending moment equation for second beam. So capital M is equal to reaction into X. That is 112X. And small m is equal to reaction, that is 0.6 into x. Since it is downward, we have to write minus 0.6x. What are the limits? From A to D means from 0 to 2 meter. And for portion AD, moment of inertia is 2I. So here we have to write 2I. Now next we will write bending moment equation for portion DB. For portion DB, you can either consider origin as A or you can also consider origin as D. So in this case, I am considering origin as D. That means we are measuring the distance x from D. So if you write the equation capital M from first figure, we will get reaction 112 into x plus 2 minus 40 and small m is equal to minus zero point 0.6 x plus 2 because we are measuring x from D. So therefore limits are 0 to 2 and moment of inertia is 2I. Now for BC portion, it is convenient to take C as origin and write the equation from right side. You know that we can write the bending moment equation either from left side or from right side. So it is convenient to use right side for portion BC. So therefore we have considered origin as C and we have written the equation from C. So it is due to load it is minus 60x square by 2 and due to reaction it is plus 248 into x. Then small m means moment due to reaction due to unit load that is minus zero point 0.4 into x. Now here limits are from C to B means from 0 to 6 and moment of inertia for this portion is 3I. So this is how we can prepare the table. After preparing table, we will develop DRL and F matrix. So let us first see how to develop DRL matrix. We know that DRL means displacement in release structure in the direction of coordinate and it is calculated using this integration mm dx upon EI. Now this is the table which we have prepared. There are three different parts in this beam that is AD, DB and BC. So we have to calculate this integration for three different parts. Either you can write a single equation or you can separately write for AD, then DB for and BC to avoid the calculation mistakes. To write the equation for AD, the limits are 0 to 2. Capital M is 112x. Small m is minus 0.6x. And moment of inertia for portion AD is 2I. So if you substitute all this, you will get minus 89.6 upon EI. Similarly, you can write the equation for portion DB and calculate the value for portion DB, which will be equal to minus 555.2 upon EI. And for portion BC, you can write the similar equation. You will get the value of integration as minus 1084.8 upon EI. Now after adding all these three values, we will get the DRL value, which will be minus 1729.6 upon EI. Next step is to develop flexibility matrix. To calculate the flexibility coefficient, we have to write the value of small m twice into dx upon EI and integrate it. We have to divide this beam into three parts. We will write a separate equation for AD, DB and BC. For portion AD, small m value is minus 0.6x. So write it twice, minus 0.x multiplied by minus 0.x dx upon 2ei, because I value is 2i for portion AD. You will get 0.48 upon ei. Similarly, you can write for portion dB. For portion dB, small m value is minus 0.6 x plus 2. So calculate the value. You will get 3.36 upon ei. Similarly, calculate for portion BC. You will get 3.84 upon ei. Now add all these three values. So after adding all these values, you will get F matrix as 7.68 upon ei. Next step is to solve this flexibility equation. Remember that in this equation, R is unknown. So if you write all the values in this equation and if you solve this equation, you will get RB is equal to 225.21 kilonewton. The value is positive, that means assumed direction is correct. RB is in upward direction. Once you calculate redundant reaction at B using flexibility matrix method, other reactions, that is Ra and Rc, you have to calculate using equations of equilibrium. So let us first calculate Ra. To calculate Ra, we will apply summation of moment about C equal to 0. You will get Ra is equal to minus 23.126 kilonewton. Negative means the reaction is in downward direction. To calculate reaction at C, we can apply summation of vertical forces equal to 0. So if you apply this condition to the complete structure, you will get Rc is equal to 157.916 kilonewton positive. Since this value is positive, that means Rc is upward. Once you calculate all the reactions, you can draw shear force diagram. Drawing shear force diagram for any beam is nothing but to move your hand in the direction of forces, that is vertical forces. So here, first we will draw a baseline. After that, at A, there is downward force 23.126. So we will move our hand in the direction of RA, which is minus 23.126. Then from point A to B, there is no vertical force, so it will be a straight line like this. At B, there is upward reaction of 225.21. So out of this, 23.126 will be below the line and above the line, it will be 225.21 minus 23.126, which will be equal to 202.084 kilonewton. After that, the force is reducing uniformly. So from 202.084, if you deduct 60 into 6, 60 into 6 is the load due to UDL. So if you deduct it, you will get 157.916 kilonewton. And there is upward force at C, which is reaction at C, 157.916 kilonewton. So this is nothing but the shear force diagram for this beam. So after drawing the shear force diagram, it is important to locate the zero shear force in this beam, because at the point of zero shear force, there is maximum bending moment in the beam. Therefore, we will locate this position. Either you can calculate by writing similarity of triangle, or you can write the general equation of shear force at section X. So I am writing by considering section X and writing the shear force equation. So if you write it at X, you will get 157.916 kilonewton. From right side I am writing 157.916, which is RC, minus force up to x is 60 into x is equal to 0. Therefore, x is equal to 2.63 meter. That means from C at the distance of 2.63 meter, there is maximum bending moment. Now the portion which is above the baseline is positive shear force and which is below the baseline is negative shear force. So this is how we can draw the shear force diagram of this continuous beam. Always write the unit. The unit is kilonewton. Once you complete shear force diagram, next step is to draw the bending moment diagram. So for that we have to calculate the bending moment values at various locations. So first of all we will calculate bending moment at the support A, B and C. You know that support A and C are the simple supports and therefore bending moment at A and bending moment at C is 0. At simple supports and simple support, the bending moment is always 0. B is the interior support. At interior support, there will be bending moment. You can calculate bending moment either from left side or from right side. From both the side, you must get same answer if your reactions are correct. So let us first calculate considering left part of B. So if you calculate from left side, it is RA multiplied by 4 minus 40. So you will get minus 132.5 kilonewton meter. Now we will calculate it from right side also, though it is not required. So bending moment at B, considering right part, so it will be RC into 6 minus total load is 60 into 6 and it will act at 3 meter from B. So bending moment is minus 132.5 kilonewton meter. After that, we will calculate maximum bending moment. We know that shear force is 0 at 2.63 meter from C. So we will write a general equation of bending moment at 2.63 meter. So maximum bending moment is at x is equal to 2.63 meter. So write the equation it from right side. So upward forces don't consider clockwise anti-clockwise while writing bending moment. Write for upward forces positive value and downward forces negative because upward forces always create sagging bending moment and downward forces always create hogging bending moment. So here we will write equation from right side RC into 2.63 minus load on portion X is 60 into 2.63 and it will act at 2.63 divided by 2 from the section. So you will get 207.81 kilonewton meter as maximum positive bending moment. So maximum positive bending moment is 207.81 kilonewton meter, which is at 2.63 meter from C. Next, we will write the equation of bending moment at D. At point D, there is a moment of 40 kilonewton meter. Therefore, there will be two values at point D, just to the left of D and just to the right of D. We will write the equation from considering left side because it is easy. So bending moment just to the left of D is minus 23.126 which is RA multiplied by 2. Don't write minus 40 here, though it is, you can see the minus 40 kilonewton meter movement acting at D, but it is at D, not just to the left of D. So it is minus 23.126 that is RA into 2, which is minus 46.252 kilonewton meter. Just to the right of D, you have to add that value of 40 kilonewton. So since its direction is similar to the downward forces, you have to write minus 40. So you will get minus 86.252 kilonewton meter. So now we have calculated all the values of bending moment. So these are the values of bending moment which we have calculated. This is the flexibility matrix method, which is a force method. In force method, we do not draw the bending moment diagram by overlapping positive diagram over the negative diagram. But here we can directly draw the net diagram. Let us see how we can draw this. First you draw the reference line. Then you know that bending moment at A is 0. So there will not be any ordinate at A. At D, just to the left of D, the ordinate is 46.252 negative. Negative values we will draw below the line and positive values we will draw above the line. So join this. At D there are two values. Second value is minus 86.252. So there will be a drop of 40 kilonewton meter at point D. Then draw the ordinate at point B, that is minus 132.50. Join this. In portion BC there is uniformly distributed load, so it will be a curve. At C, we know that bending moment is 0, and at 2.63 meter, there is maximum positive bending moment, which is 207.81. So join this using a curve line like this. So this is the bending moment diagram, and unit is kilonewton meter. Once you complete this, you have to locate, or you have to find out the position of point of contraflexure. Point of contraflexure means where bending moment changes its sign from positive to negative or negative to positive. This point is also very important for the structural design. So we will locate now the point of contraflexure. From the bending moment diagram, we know that point of contraflexure lies in portion BC. Therefore, we will take a general section X and write down the general equation of bending moment for portion BC. So it is convenient to write the equation from right side. So let us write the equation to calculate position of point of contraflexure. So equate bending moment at X is equal to 0. Bending moment at X from right side is RC into X minus load is 60 into X by 2 is equal to 0. So therefore, we will get X is equal to 5.264 meter from C. So here I have shown the point of contraflexure, which is at 5.264 meter from C. This is how we can draw shear force diagram and bending moment diagram of a continuous beam using flexibility matrix method. This is the final answer which is expected in examination. So stay connected to watch next video of same problem by moment distribution method. Thanks for watching.